So today I'm going to try to explain electrostatic potential energy, which is the potential energy at a point within an electric field that is generated by stationary charges. So let's get started by explaining what an electric field is. So imagine you have some positive charge. Now it's not moving. That's electrostatics. Uh, Positive charge will generate some field in all directions in a circle or a sphere around it, operating like pointing outwards. And the equation for an electric field at some point is a vector 1 over 4 pi epsilon naught. This is also the value for K from Coulomb's constant, and it's multiplied by Q over R squared times R hat, which is the unit vector in the direction of the point. So Q is the charge that's generating the field, and R is the distance that the point in space is away from that field. Now, let us begin our discussion of energy. And there is no talking about energy without first talking about work. So, work defined in mechanics is just equal to force applied to an object times the distance that the object has moved. This is the mechanics definition. We're talking about electrostatics, so it's going to be slightly different, but pretty much the same idea. Let's say we have 2 points in space, point A and point B, and we want to move a charge along some path from point A to point B. Let's say we have the charge Q, and we apply some force F, and this is our displacement vector ds. So our equation for work is going to be W is equal to an integral from point A to point B times the force that we apply times the displacement vector. So the force applied to this small infinitesimal displacement vector, and that's going to be done for every point along the path from A to B. Now, this work is negative because we're defining potential energy in the electrostatic or in the electric field where the max energy is equal to 0, and that means that everything has to be below 0, so every potential energy at every point is going to be negative. Now, we can take this equation and let's make it a little bit more simple. Let's say W on a unit charge. So that will give us pretty much the same thing, the integral from A to B, but now we have the electric field. And yeah, so this is the force generated by the electric field on the particle because we're using a unit charge. So that makes it simple because now we can just plug in the formula for the equation for the electric field, which is Q over 4 pi epsilon naught times 1 over R squared. And I'm going to drop the unit vector for now. Now, this we can remove, or we can take this term out of the integral because it's not related to the integration variable. Integration variable, is dr because now our displacement vector is in terms of r. So we can write this as negative q over 4 pi epsilon naught times the integration from a to b of 1 over r squared dr. And if you do this integration, it's not the most complex integration, but you will end up with negative q over 4 pi epsilon naught times 1 over RA minus 1 over RB. And that's just because we're applying these limits to the integral. Yeah, so we can see from this equation that our equation for work, our equation for work is independent of the path taken from A to B. So we could have taken this path, we could have taken some other path, and our equation for work is only dependent on the endpoints. So where are point A and where is point B? And because of that, we can write down a nice formula for basically the potential energy at a point. We can use phi at a point, well, let's say phi at point A is equal to Q over 4 pi epsilon naught times 1 over RA. And then we can write this equation for work, which is still equal to the negative integral from A to B of E ds, but we can now write that as phi of B minus phi of A. And if we expand this using this definition for phi, we'll end up with Q over 4 pi epsilon naught times 1 over RB minus 1 over RA. And you'll notice that this is the same equation that we got here. We just swap this negative symbol and turn these signs around and we get this same answer. So now we have an equation for work in terms of this function phi, but we can actually simplify this more because we can say that phi at some point P that we're interested in minus some source point P naught is equal to the same integral, but this time from P naught to P of E ds, and this thing is negative. But if we're careful about how we choose this point P naught, in particular, let's say we have this charge generating an electric field, and we want to choose our point P naught to be a distance of r is equal to infinity away from our source charge. And if we do that, because we have here that we are basically phi is proportional to 1 over r, if we have 1 over r, in this case is infinity, this is just 0, which means we're multiplying this term by 0, and that just means that this thing goes away. And then we can just write phi of p is equal to this integral from P naught to P of E ds. And this makes our lives, well, it simplifies things a little bit because, well, phi of P is just a point, so we can write phi of x, y, z is equal to, again, this integral from P naught to P of E ds. But if we differentiate both sides, we can say that d phi dx is equal, or sorry, d phi dx, d phi dy, d phi dz, and if you differentiate an integral, you basically just cancel the integral, so we have this equal to negative e. And this term, well, this term is basically just the gradient of phi, so we can write this as grad phi is equal to negative e, and in particular it's probably more useful to say that e is equal to negative grad phi. This is the important equation. It just says that you can calculate the electric field by first calculating phi, which is the electric potential in your static system, and then taking the gradient. And again, that is useful because it's easier to calculate phi than it is to calculate the electric field directly, and that is because Richard Feynman says so. So don't trust me, trust Feynman. Goodbye.